In section 7.3, we're going to go further about correlation into the details about the best fit lines and the predictions which can be made with these things. And so at the end of the last section, I showed the correlation done through Desmos. And we created a line through the scatter plot, I should say. This is what we're going to be calling the line of best fit, in the sense that this line passes through the data points and lies closer than any other straight line that we could draw through the data. So it best fits where the data is going. The best fit line shows up as close to the data points as possible. Some might fall farther away from this best fit line, but we're trying to position it in the most optimal place to fit the data. So the definition of the best fit line, also this thing is called the regression line. On a scatter point is a line that lies closer to the data points than any other line possible according to the standard statistical measures of closeness. We can make predictions with the best fit line, but there are a few cautions we need to keep in mind when doing this. Don't expect a best fit line to give a good prediction unless the correlation is strong and there are many data points. So we shouldn't use a best fit line to make predictions when there's no correlation, and also in cases where we have not very many data points. So if the sample points lay very close to the best fit line, the correlation is very strong and the prediction is more likely to be very accurate. If the data points lie far away from the best fit line, the correlation is probably weak and the predictions will be much less accurate. Another thing is we don't use the best fit line to make predictions beyond the bounds of the data points to which the line was fit. A best fit line based on past data also is not necessarily valid now and might not result in valid predictions for the future. Also, we don't make predictions about a population that is different from the population from which the sample was drawn. So remember that a best fit line is meaningless also when there is no significant correlation or when the correlation relationship is nonlinear. And so here's an example of that. This is, again, going back to life expectancy and infant deaths. We notice that we have our best fit line, which follows the trend downward as infant mortality decreases and life expectancy increases. However, we can't keep following this line beyond this because it'll go down into negative territory, which would indicate negative mortality rates. So we can't use this line to make predictions for that reason. On this example, we're going to look at a few scenarios and look at whether the prediction or implied prediction should be trusted and explain why or why not it should or should not be trusted. First situation here, it says you found the best fit line for the correlation between the number of hours per day that people exercise and the number of calories they consume each day. You've used this correlation to predict that a person who exercises 18 hours a day would consume 15,000 calories per day. Well, there's several reasons why this could be incorrect, but one main reason is no one would possibly exercise 18 hours a day on an ongoing basis. So it seems like we're going to a little too extreme for a number like 18 hours a day. So a prediction like that really couldn't be trusted for that reason. Another situation here says there's a well-known but weak correlation between SAT scores and college grades. You use this correlation to predict the college grades of your best friend from her SAT scores. In a situation like this, notice the keyword weak correlation. The fact that the correlation is weak means that we should not expect very great accuracy if we use this correlation to make a prediction about a single individual. Few other situations. One here says historical data have shown a strong negative correlation between national birth rates and affluence. That is, birth rates and wealth and things of that nature. So what that would also mean is countries with greater affluence, greater wealth, and so forth tend to have lower birth rates. This data is used to predict a high birth rate in Russia. Well, the prediction here cannot be automatically assumed that the historical data still applies today. In fact, Russia has very low birth rates despite having a fairly low level of affluence and wealth in general. So the prediction really doesn't hold true for those reasons. Another situation here says a study in China has discovered correlations that are useful in designing museum exhibits that Chinese children enjoy. A curator suggests using this information to design a new museum exhibit for Atlanta area school children. Well, in this case, there are cultural differences that might make a prediction untrustworthy as a result. So what we have in the one country might not apply the same way it would in another country. A couple more scenarios here. One says scientific studies have shown a very strong correlation between children ingesting lead and mental issues. Based on this correlation, paints containing lead were banned. In this case, however, given the strength of the correlation that they had and the severity of the consequences, this prediction and the ban that followed seemed to be reasonable. In fact, with more information and later studies, they actually established that lead was an actual cause. So that correlation did connect to a cause and effect relationship. And then one other one here says, based on a large data set, you've made a scatter plot for salsa consumption per person versus the years of education. The diagram shows no significant correlation, but you've drawn the best fit line anyway. The line predicts that someone who consumes a pint of salsa per week has at least 13 years of education. Now, this seems like a fairly untrustworthy prediction because there's no significant correlation. The best fit line and any predictions made from it are meaningless. Here's another example of using best fit lines to make predictions that don't quite work out. It says the figure shows the data and best fit lines for both men's and women's world record times in the 1 mile race. Based on this data, predict when the women's record would be faster than the men's world record. Well, if we look along here, it looks like the lines will meet somewhere in the 2030s, 2040s. If we just follow the best fit line from the last world records until the lines meet. So, somewhere in the late 2030s, let's say. But would that be a good thing to try to predict this way? This prediction would indicate that world records should continue to fall. However, looking at it, none of the world records have changed very much in several years. So the prediction is not really going to be valid because at some point the records are going to be harder and harder to try to improve upon, and at some point they may not really be able to improve upon them much more. So this prediction is not valid since it can predict to impossibly hard to reach or impossible to reach records. So we can't really use the best fit line to make that prediction. Okay, another subject about best fit lines, and going back to the correlation coefficient R. The square of the correlation coefficient, or R squared, is the proportion of the variation in a variable that is accounted for by the best fit line. So what that means is we can get an idea of how well the best fit line accounts for the data by doing the square of the correlation coefficient, R squared. So here's an example. It says, you are a manager of a large department store. Over the years, you found a strong correlation between your September sales and the number of employees you'll need to hire for peak efficiency during the holiday season. The correlation coefficient is R equals 0.950. So that means higher September sales corresponds well with higher amount of employees during the holiday season. So this year, your September sales are fairly strong. Should you start advertising for help based off of this correlation coefficient and the prediction made by the best fit line? Well, if we square the correlation coefficient, R squared is the square of 0.950, which is equal to 0.903, or as a percentage, 90.3%. What that means for us is this means that about 90% of the variation in the number of peak employees can be accounted for by the linear relationship found in the best fit line. So about like 90% of the time, the best fit line is accounting for the number of employees needed. So the best fit line, if that's 90%, it's going to be a fairly well for predicting and accounts for the number of employees needed. So it would be a reasonable prediction based off of this calculation. So this can help us understand how well that best fit line is going to work as a predictor. A higher percentage, the better the best fit line takes into account the data. Here's another example. It says data collected in presidential election years since 1964 show a very weak negative correlation between voter turnout and unemployment rate, with a correlation coefficient of about R equals negative 0.1. Now, if we square that to get negative 0.1 squared, it'll turn into 0.01, which is just 1%. So what that tells us is the best fit line for this data only accounts for 1% of the variation in voter turnout, and so it would not be a very reliable predictor to use the unemployment rate to predict voter turnout. And one reason for this is the correlation is very weak, negative correlation, because our R value is very close to 0. So for that reason alone, using unemployment rate to correlate with voter turnout will not give very good predictions. So one important thing to discuss now that we're talking about the best fit line is that the equation of any straight line can be written in the form y equals mx plus b, where m is the slope and b is the y-intercept of the line. So the formulas for slope and y-intercept of the best fit line are given here. We're not really going to use these formulas, but this is how it's calculated. R is the correlation coefficient. Sx denotes the standard deviation of the x values. Sy is going to denote the standard deviation of the y values. X bar is the mean of the x values, and y bar represents the mean of the y values. Using this, we can calculate m and b, and m and b are going to give us the equation for the straight line, which turns into the best fit line for the scatter plot. Now we're going to use technology to come up with this equation for us so that we have the equation of the best fit line at our disposal. So here's a data set we're going to use. It says listed below are altitudes in thousands of feet and outside temperatures in Fahrenheit recorded during Delta Flight 1053 from New Orleans to Atlanta. We're going to construct a scatter plot and best fit line. We're going to calculate the correlation coefficient R and R squared. And that'll tell us if there's any correlation, if it's strong or weak. We'll be able to see how well the best fit line matches the data, and we can also look to see if there are any outliers and if they affect the best fit line and so forth from there. And finally, whether or not the best fit line could be used to reasonably predict within the range of the given data. So I've pulled up Desmos here again. At the end of section 7.2 video, I also did this as well. I created a table to put the data values in. And now once I've put those data values in, I can now see this scatter plot. Now, if you put these in without anything else done, it's not going to show up probably very well. So what I had to do is go up here to this gear icon again, and I had to put in the numbers for X and for Y, for the lowest X value and the highest, and the lowest Y value and the highest Y value. Just looking at the numbers in the first column, I figured out, well, the lowest value is a 3, so why don't we put a 0 here at the low end? The highest value is a 33. So why don't I put a 35 here? Just a little extra space to make sure they all fit. And I did the same for Y as well, since negative 55 is lower than anything else for these Y numbers. 60 is bigger than any of these other numbers. Once I put those values in here for the highest and lowest X values and Y values, it should be able to show up the full scatter plot. Now we can see how the trend looks downward and the points are lined up pretty well. Now if we want to come up with a correlation coefficient and best fit line using Desmos, what we do is we click over here in a blank spot, we type Y1, and notice the 1 automatically is going to go down below. It automatically does that. And then I push this little curly line here on the keyboard, that's called tilde, and I do mx1 plus b. And that's the equation of a straight line that was mentioned in the slides. And as soon as I do that, it comes up with r squared and r, and also shows me the best fit line as well. Shows me what the number for m should be and the number for b should be inside of this equation. So just to discuss what we now have here from our best fit line and scatter plot, the best fit line does match the data very well. There's no major outliers. And again, over there it tells us what the R coefficient is. Here in the Desmos, told us that it's negative 0.9968. So since it's negative correlation. It's very close to -1, so it's a very strong negative correlation. So like I mentioned, all points are close to the best fit line with no major outliers. And as a result of that, the best fit line can be used to predict temperature at a given altitude. Higher altitudes corresponding to lower temperatures, at least within the range of altitudes that we usually fly out with commercial aircraft and so forth. And finally, we can also get the equation for this best fit line by looking at the M and B numbers. So this is the equation of the best fit line.